Okay, Mrs. Howard's Pre-AP Chemistry, Unit 9, Stoichiometry, Part 3, and get ready because we're going to cover several math concepts right in here. Take out your 8 pages, take out your periodic table, get your calculator, get a scratch sheet of paper, get your notes out, get it all ready because we're going to go fast here. Alright, so we did some mass calculations. We went from moles of one substance in a balanced chemical equation to moles of the other. We can go from mass of one substance in a balanced chemical equation to mass of another. We can also do volume calculations. And this is when we first started really working with gases. Now, the big key here is that we can only use this 22.4 liter thing if we're at STP. STP, standard temperature and pressure, 0 degrees Celsius, 1 atmosphere. Alright? STP. So, our question first starts out, how many liters of CH4 at STP are required to completely react with 17.5 liters of oxygen? Right, so we have to have a balanced chemical equation. So we've got the combustion of methane, and we've got a balanced chemical equation. It's like 1 mole of methane plus 2 moles of oxygen yields 1 mole of carbon dioxide and 2 moles of water. Alright, start off, write down what they gave us. So they gave us, in the problem, 17.5 liters of oxygen. We can't do squat with anything but moles. So whatever substance you have first, you've got to get it into moles. And the key here, the conversion factor here, is going to be that 22.4 liters. If we have any gas at STP, then if you have 1 mole of it, it's going to take up 22.4 liters of volume. So that's our conversion factor. That's how we get rid of the liters and change to moles. Now, once we have it in moles, then we can go on from moles of one substance to moles of whatever else is in the balanced equation that we want. So, in this case, we're going to go from moles of oxygen, and if you look at the problem, it says how many liters of CH4. So for every 2 moles of oxygen, if you look on the balanced equation, there's 1 mole of CH4. So if we were to stop right here, our answer would be in moles of CH4, because notice the liters of oxygen cancel out, the moles of oxygen cancel out, so we've got moles of CH4. But they want our answer, they say how many liters. So now we use our other conversion factor, and we have moles, 1 mole of CH4 is equal to 22.4 liters. So we put that in there. Notice what cancels out. So this is going to make your life much easier when you get accustomed to using this. Right. So anything concerning these two steps, notice they're just the opposite of each other. So 22.4 liters on top, 22.4 liters on bottom, you've got it canceled out. What that means is you can look at that balanced chemical equation, and if you're at STP, instead of looking at it as moles of substances, you can also look at it as liters of substances. So you can go straight from 17.5 liters of oxygen to however many moles of CH4. Using the mole ratio, you just think of it as liter ratio. It only works when you're dealing with gases at standard temperature and pressure. Okay, how do we know this? Because old Avogadro, he's the guy that figured out, hey, if you've got equal volumes of a gas at the same temperature and pressure, they contain the same number of particles. Moles are numbers of particles, yes? 1 mole has 6.02 times 10 to the 23rd particles, so it works nicely. What that means is you can treat reactions as if they happen in liters at a time, as long as you keep the temperature and the pressure the same. Specifically, you're going to keep the temperature and pressure the same, but we want to make sure we know exactly how many what volume it is, so we say specifically at STP. And that way we know that at STP, we've got 22.4 liters. So, and you guys know this already, if you change the temperature of a gas, isn't it going to expand? They take up bigger volume. So that's why we indicate STP. That's where we know it's at 22.4 liters. Okay, so we can take a shortcut for that same volume problem. How many liters of CH4 at STP are required to completely react with 17.5 liters of O2? Exact same problem we just had, but we take a shortcut. And what we do is we say 2 liters of oxygen for every 1 liter of CH4. So we're looking at that balanced equation. Instead of treating it as moles of oxygen, we're treating it as liters of oxygen and liters of CH4. And yes, it's, instead of doing the nice little dimensional analysis, picket fence, it's just a little bit differently. It has a different look to it right there, but it's the exact same thing. You could put it in the little dimensional analysis grid. And most of the time I do, but someone else wrote this, I just modified it, and apparently I didn't modify this section. So if you look here, our liters of oxygen cancel out. All we have left are liters of CH4 as our unit of measurement. This only works with volume problems. That's the only one it's going to work with. It will never work with anything else, just volume problems when it's an STP. So don't get too carried away with this process. Alright, the next concept besides the volume reactions is limiting reagent. What if you have two substances and you just smash them together and say, hey, look how much stuff we're going to get? Well, one of them is probably going to run out before the other one does. So here's your example. If you're given 1 dozen loaves of bread, a gallon of mustard, and 3 pieces of salami, how many salami sandwiches can you make? Well, considering we only put 1 piece of salami per sandwich, then we can make a max of 3 sandwiches, right? Doesn't matter if we have a whole dozen loaves of bread or a gallon of mustard. We only have 3 pieces of salami. So the salami is the limiting reagent or the limiting reactant. That word reagent is another word for reactant, or it's just a different term for it. So it's the reactant that you're going to run out of first, and it limits how much stuff you're going to make. So the salami limited how many sandwiches you can make, so it limits your product. The one that you have left over is called the excess reactant or the excess reagent. It's the one you've got left over. The limiting reagent determines how much product that you can make. That's incredibly important. Limiting reagent determines how much product that you can create. Make sure that you've written this down on your notes. Make sure you put a big star beside these words because these are really important terms, and we'll be doing a lot of this stuff throughout the rest of the school year. You're never getting away from this stuff again. How do you find out which one is the limited or the limiting reagent? You have to do 2 stoichiometry problems. Yes, it's work. So the one that makes you do 2 separate problems, so you've got 2 reactants. You find out using this reactant, if we started out with 15 grams of this reactant, how much product it would make. Then you do another problem. You say, hey, we started out with 12 grams of this reactant. Let's find out how much product it makes. Whichever one makes the least amount of product, that's how much stuff you could possibly make, and that substance that you used is going to be the limiting reagent. Okay, so here's your problem. If 10.6 grams of copper react with 3.83 grams of sulfur, how many grams of product, that's copper 1 sulfide, will be formed? All right, so we have the balanced chemical equation. We have to do this. So we've got 10.6 grams of copper, and we've got 3.83 grams of sulfur. Right, so what we have to do is we have to start off with, let's say, 10 grams of copper, and we have to figure out how many grams of the sulfide will be formed. So 10.6 grams of copper, and again, that should be 63.5 grams of copper, but I didn't write this out, so I just forgot to modify that stuff. So we went from grams of copper to moles of copper. Now we go from moles of copper using the balanced equation to moles of copper 1 sulfide. And then we go from moles of copper 1 sulfide to grams of copper 1 sulfide. And we find out that we've got 13.3 grams of copper sulfide produced. Yes? All right, so are we sure that's how much is produced? No, because we've got only 3.83 grams of sulfur. So we do the exact same problem, only we're going from sulfur to the copper 1 sulfide. So the same problem, 32 grams of sulfur per 1 mole, so we change from grams of sulfur to moles of sulfur. Then we change from moles of sulfur to moles of copper 2 sulfide. Then we change from moles of copper 1 sulfide, to grams. So we're changing from grams to moles of one substance, moles of another, from moles of that substance to grams of the substance. And we find out with our second problem that we get 19.0 grams of copper 1 sulfide. I have hiccups now. All right. So looking at this, you're saying, okay, the first one we only could make 13.3 grams. And the second one, even though if you look in the original problem, we have less of the sulfur than we have of the copper, that's not how you determine the limiting reactant. Which one is used up first? And to do that, if we use every single bit of that 10.6 grams of copper, the maximum Cu2S that we can make is 13.3 grams. We don't have enough of the copper to make this 19.0 grams of copper sulfide. So the one that's going to run out first is the copper. And if you look right there then, copper is the limiting reagent because we run out of it first. And we know that because when we did our 2 stoichiometry problems, which one of those two reactants created the least amount of reagent, or the least amount of product, and that's the copper. Okay, another example. What if we have 10.3 grams of aluminum and we react it with 51.7 grams of copper sulfate? How much copper is going to be produced? So we're going to have a single replacement reaction, so the first thing you have to do is write out the balanced equation. They're asking us how much excess they're asking us more than one question here. So let's see, do I need another thing? Okay, so let's go back here and let's work this out. I'm going to go back one here. And let's work this out, see if my pen works, see if I can't keep this from screwing up. Alright, there's the pen. Okay, so 10.3 grams of aluminum. And I want to go from, I messed up. I don't have my balanced chemical equation right up here. So I have aluminum plus CuSO4 yields copper plus Al2SO4 3. And then I have to balance my equation. So I'm going to have to get, let's start off, let's put a 3 over here and get, stop that. Let's put a 3 over here. So 3 coppers, 3 sulfates, and looks like a 2 right here. Is that right? 2 aluminums, 3 coppers, 3 sulfates, 3 sulfates. Alright, so now I come back down here to my problem and say, okay, for every 10.3 grams of aluminum, I've got aluminum on the periodic table is 27 grams. It's 27 grams of aluminum, and that's for every 1 mole of aluminum. Now I've changed it to moles. Now what I want to do is they want to say how much copper is produced. So I want to go from moles of aluminum to moles of copper. So for every 2 moles of aluminum, I have 3 moles copper, and I'm going to convert it to grams. So for every 1 mole of copper, write this down if you're not writing it down now. If I can write it down, you can write it down. You've got 1 mole of copper, and the formula mass for copper, or the molar mass for copper, is 63.5 grams of copper. Let's see what cancels out. Grams of aluminum, moles of aluminum, oops, I didn't write it there, did I? Moles of aluminum, moles of copper, and all I have left over here, my answer is going to be in grams of copper. So pop it into your calculator. 10.3 times 3 times 63.5 divided by 27 times 2. And I've got 36.336. Check that. I might not be right. Check my answers. Make sure you guys got the same thing. 36.336 grams of copper. Then we do the exact same problem with the copper sulfate. So 51.7 grams of CuSO4. And what's the formula mass for copper sulfate? 63.5 plus 32 plus 64, is that right? 159, if I'm wrong, fix it on your paper. 159 grams of, and I'm running out of space, CuSO4, and that's for 1 mole of CuSO4. I know, it's ugly. Alright, so now I need to change from moles of CuSO4 to moles of copper. So for every 3 moles of CuSO4, how many moles of copper do we have? Ooh, 3 moles of copper. And now I just have to change it to 1 mole of copper to 63.5 grams of copper. So moles of copper cancel out, moles of CuSO4 cancel out, grams of CuSO4 cancel out. And look at the 3 and the 3. I can cross out that 3 and 3 because why am I going to put extra work for myself? So this should be in grams of copper. So pop it into your calculator. 51.7 times 63.5 divided by 159.5, and we've got 20.583 grams of copper. Which one is the least amount? Right here. Yes? Okay, so how much copper will be produced? 20.583 grams. Which substance is the limiting reagent? It's the copper sulfate that we're going to run out of first. Now the other question that was on there was how much of the excess reagent will be left over, right? So how many grams did we use? We're going to have to work one more problem, yeah? So we're going to have to figure out if I have, take your limiting reagent, so I'm going to erase, let me see if I can erase this stuff easily. Get the little eraser. I'm just going to erase one of these. Let's just erase this one up here. Oh, isn't that just spiffy? Okay, so I'm going to go back to the 10. Now, I know that I'm going to make this 20.583 grams of copper. How much of that unlimiting reagent, how much of that aluminum is going to be left over? Well, I'm going to start off with my copper sulfate because I know I'm going to use it all up. So I have 51.7 grams of the CuSO4. And I'm going to start this kind of like the one on the bottom, 159.5 grams of CuSO4 for every 1 mole. So now I've changed it to moles. Again, you can't do anything unless you've got it in mole form. You can't change from one substance to another except on the mole form. So now I'm going to go from moles of copper sulfate to moles of aluminum. So for every 3 moles of copper sulfate, I've got how many moles of aluminum? From the balanced equation, 2 moles of aluminum. And then I have to go to grams. So 1 mole of aluminum is equal to 27 grams of aluminum. That's Al. Alright, so pop it into your calculator. Oh, wait, what cancels out? See if we've got it right. Grams of copper sulfate, grams of copper sulfate. Moles of copper sulfate, moles of copper sulfate. Moles of aluminum, moles of aluminum. And all we have left are grams of aluminum. So we've got 51.7 times 2 times 27 divided by 159.5 times 3. Are you using parentheses? And I got 5.834. 5.834 grams of aluminum. So if we use up all of the 51.7 grams of copper sulfate, we will only use 5.834 grams of aluminum. So they gave us 10.3. So plug your numbers in. 10.3 minus the 5.834. And what do you have left over? You have left over 4.466. Left over. Okay? Now I'm going to go back through and erase this. So if you want to pause this, pause it, but I'm going to erase right now, so get ready. Okay. So our second question was how much excess reagent remained. Right. So that was how we got all that nasty stuff in there. Now, the next thing is when we talk about the concept of yield, and it's a lot different than what it is in your driver's ed class. Concept of yield is how much product is made in a chemical reaction. So when we have the little arrow, the yield sign, that's what we're talking about. What's yielded? How much stuff is produced? You can have your actual yield, and this is what you get in the lab. A lot of times this is called the lab yield. It's what happens in the real world when you're back in the lab, how much stuff was produced. You also have the theoretical or calculated yield. Then this is what the balanced equation is. It tells you what you should have. And then the other yield that you're talking about is your percent yield. And that's where you're comparing the actual and the theoretical. This is what you really made in the lab, divided by what you're supposed to make in the lab, times 100, and that's your percent. What percent of the theoretical, the calculated stuff that you actually create in the lab? And that's the third piece that's involved in here with your student expectations for this section. Look at your pretty student expectations on the board. Aren't they lovely? Okay, so you've got 6.78 grams of copper produced when you've got 3.92 grams of aluminum that react with excess copper 2 sulfate. So our balanced chemical equation, 2 moles of aluminum plus 3 moles of copper sulfate yield 1 mole of aluminum sulfate plus 3 moles of copper. So what is the actual yield? 6.78 grams of copper is produced when you've got 3.92 grams. What's the theoretical yield? And then what's the percent yield? So usually in the problem, they'll tell you, hey, that 6.78 grams, that's what we actually got in the lab. So they'll indicate to you, this is what we happened in the lab. So usually the actual yield is just given to you in the problem. The theoretical yield, now what you have to do is you have to take that 3.92 grams of aluminum, because that's the one that's going to limit it, because the other one says it's got excess, you've got tons of it. So do a mass problem. 3.9 grams of aluminum, and figure out how many grams of copper you were supposed to be able to make, and then use your percent yield equation. You'll find this, and I think it's on page 3 of your 8 pages, but you'll find these equations on here, and we will do plenty of problems to give you practice. The percent yield basically tells us how efficient the reaction is. How efficient were you in the lab? How many errors did you make in the lab? The more errors you make, the more stuff you spill and stuff you lose, the lower your percent yield is going to be. You can't have a percent yield bigger than 100. I mean, you can't make more stuff than what you've calculated, because in your calculations you're using the maximum amount. If you do come up with an answer like you're doing percent yield and you figure out, oh my gosh, I've got more than what I was supposed to have, it means there's an error in there. You've got more stuff in your container that you were measuring than what you expected to have in there. So the theoretical yield will always be larger than the actual yield. However, you notice there's a little note down there. Due to impure reactants, competing side reactions, loss of product and filtering or transfer between containers, and when you're measuring, you'll always have some weird things that happen, right? So we're going to do a lab where we do percent yield, and we figure this out, and you'll find that, yeah, there are going to be some people that somehow end up with more than what they were supposed to have, and usually that's because the stuff that they have left over in their container that they're saying is 100% pure, this product, really has a lot of extra stuff inside there. Okay, we're finished with this section. Let's work some problems.